Okay, sorry about that. Welcome everybody. Like Audrey said, we're in a third-part series here on lyophilization. Today we're going to dive into some of the scientific principles behind the cycles, specifically freezing, annealing, primary and secondary drying, and what's really important about each one of those. Certain products are a little bit more picky than others and do require some more attention. So we're kind of going to walk you through what's going on behind each of these phases of the cycle, why we might need to pay particular attention to one phase more than another. Okay, so let's first get into freezing and what's going on in the freezing process. So basically, I believe we covered this the last time in thermal characterization topic. So basically, we're taking a product that we formulated. It's got all our additives, all our excipients, anything else in the formulation that we need to help stabilize it, give it good structure, and then we start cooling it. So we load it in the freeze dryer and start reducing the temperature of the shelves. Well, we hit a point, like we mentioned last time, where we're going to get ice crystal nucleation. So we get two water molecules come together. It's going to be at some sub-zero temperature. We get two water molecules together, come together, form a stable nucleus, and boom, we get nucleation of the ice crystals. Now again, this is H2O only, pure water. Everything else in the formulation is pushed around those ice crystals in what we call the interstitial space that we did talk about last time. As we continue to go down in temperature, those little the nuclei continue to grow and form crystals, and they do that by pulling the moisture or the water out of the interstitial space, where we do see that solute concentration that we talked about before. So again, everything is super concentrating in our formulation. Finally, we hit a temperature and a concentration where one of a couple different things is going to happen. We get glass formation that we talked about last time. If it's not going to crystallize, we may get a stable glass, or we may get an unstable glass or a metastable glass, which we've talked about last time. If the solute's going to crystallize, then it will go ahead and form that eutectic. So again, the eutectic, if we recall from last time, is two or more crystalline species that are in such close contact that they melt like a single pure substance. One of the crystal forms may be your active ingredient. It may be an excipient. The other crystal form is going to be tiny ice crystals that combine with that to form that eutectic. Now, why don't things freeze at 0 degrees C? We know everything, ice melts at 0 degrees C, but there's a couple of reasons things don't freeze at once they cross the 0 degrees C line. One is freezing point depression. Anytime we add solute to water, we alter the freezing point of the water. And then something called supercooling, which we'll talk a little bit about as we go through this process. So we need to be aware of these during cycle development, as these can impact stability and how the product behaves in the freeze dryer. Now generally, we'll pick this up on the DSC when we run the initial scan. Again, I mentioned last time there's two curves that we deal with in DSC. One's a warming curve, one's a cooling curve. We'll look at the cooling curve, but we don't use it for any calculations. And again, it's because of these things, freezing point depression, supercooling. It's never going to freeze at the same temperature. Now, things will always melt at the same temperature, but never freeze. Now, I do look at it specifically for where that freezing or nucleation is occurring. Generally, most of the stuff I work with in our lab is going to freeze somewhere between -10 and -20 degrees Celsius. Okay, I look at it, great, there's the freezing curve. Cut it off, don't look at it again. Now the problem becomes if we've got something that's got a very, very low freezing point. Sometimes these things don't start to crystallize or freeze until -40 or -45. Then you got a problem. If you can't freeze it, you can't freeze dry it. So we do look at it, but we don't use it for any calculations. So this just shows you, again, the two curves on our DSC scan. So the bottom curve is our cooling curve. Boom, there's crystallization, nucleation, crystallization. Probably about -17 is my guess from looking at this scan. We continue to cool down. The top curve is our warming curve, and boom. This is where we're melting that crystallization, or the crystals that we form. Notice the difference in temperature. this temperature will fluctuate. Again, there's a number of different factors what causes that to change. This will always be the same. So we look at this curve, where does it crystallize? Then we throw it away. We use the warming curve, the melting curve, the glass transition for making our calculations. Again, if you recall from last time, shape of the curve, what is it? Temperature of the event, again, glass transition temperature, eutectic melting temperature. So, freezing point depression results from a change in the escaping tendency. Now, what do we mean by that? Well, if we talk about escaping tendency, we've talked about vapor pressure in the last lecture. Everything has a vapor pressure. How easy is it for the molecules in a liquid to vaporize and go into the headspace? We did talk about the contrast between water and ethanol. Ethanol has a higher vapor pressure, so it's got a higher or an easier escaping tendency. So it's easier for those ethanol molecules to escape. It's more volatile. Okay. The escaping tendency will change as we add solute to our formulation. So active ingredients, excipients, anything we add is going to alter that escaping tendency, because sometimes, well, most time it's going to hold on to the molecules, make them harder to escape. Sometimes it makes them easier. We'll say a little bit about what we mean by the triple point. We haven't looked at this yet, of a phase diagram of water. That'll make a little more sense. So we consider the interaction of solute and solvent molecules and how that changes from getting the water molecules to evaporate from the surface. And what we're dealing with here is we're not dealing with water, we're dealing with ice, and it's the same issue. So this is what's called partial pressure diagram, explained by Raoult's law. So if you think back to your physical chemistry days, you talked about the total pressure as the system is comprised of the partial pressure of whatever you're using and the mole fraction, or essentially the amount of substance that's in there. So the only thing I could find when I wrote this was benzene and ethylene chloride. Hopefully we're not freeze-drying with too much of this, but you can see the mole fraction and the partial pressure contribute to the overall total pressure of the system. What we're dealing with a lot in freeze-drying is we actually see a suppression of the total vapor pressure. The reason for that is we start talking about adhesive forces between A and B. So cohesive forces are between A and A. So the forces that attract A and A, so let's say water molecules, two water molecules, A and A, there's certain cohesive forces that hold on and bind those two to each other. We know that these are actually pretty strong for water because water has a high surface tension. So if you put a drop of water on a surface, you'll notice you'll get essentially a ball, okay? You put a drop of ethanol, it's going to flatten out pretty quickly. So again, the adhesive forces, or sorry, the cohesive forces between water and say ethanol, water is much tighter, much stronger cohesive forces. Now what we're talking about with added solute, we talk about adhesive forces, okay? So we say, well, excipient A and water molecule B have certain adhesive forces, okay? Now in this case, what's happening is the adhesive forces between A and B, the water molecule and our excipient, start to drag down the cohesive forces. So it makes it much harder for the water molecules to escape. So it's actually tying the water molecules up and binding them. So we see this decrease in the vapor pressure from the ideal, which we show again according to Raoult's law. Phase diagram of water. I don't think we touched on this the last time, but everybody knows that water exists in three different forms, and we can change those forms by altering the temperature. So we start with a liquid at room temperature, we cool, we get a solid once we get somewhere below zero, we warm the liquid up above 100 degrees, we get vapor in the form of steam. Now what I'm telling you, and according to this, we can also change form simply by changing the pressure. So I can take water at room temperature, decrease the pressure or increase the vacuum, get that water to boil at room temperature, okay? And as we continue to decrease the pressure, we can get that to freeze at room temperature. Now what's going on in freeze drying? Well, we start as a liquid, So we'll say about 25 degrees C, 1 atmospheric pressure. We decrease the temperature. Boom, we go from the liquid liquid state to the solid state. We know that. Now, we decrease the pressure or increase the vacuum. We're still in the solid state. But what if we warm? Now we go directly from the solid to the vapor state. Now, what's unique about this, or not unique, but what we'll notice from this is that there are different combinations of temperature and pressure where, say, liquid and vapor exist in equilibrium. Same thing with solid and vapor and liquid and solid. So there's different combinations of temperature and pressure where these forms can exist, okay? However, you'll notice the triple point. There's only one temperature and pressure where water exists in the solid, the liquid, and the vapor state in equilibrium. One temperature and pressure. That's at 0 degrees C. Actually, that looks like it's a little higher on my graph. And 4.5 millimeters of mercury. Now, what we're saying, okay, this is, again, a phase diagram. So at normal water, okay, this is our normal triple point. Now, what I'm saying is we add solute to our formulation. So we take water, we start dumping in excipients, active ingredients. Well, we change the vapor pressure or we lower the vapor pressure, okay? If we lower the vapor pressure, we essentially shift down, okay, the pressure. Well, since there's only one temperature and pressure, again, the triple point, the temperature has to shift as well. Okay, so we go from T0 to T. Okay, so we've shifted that temperature of the triple point. Okay. So by rearranging Raoult's law, we see the partial pressure is actually equal to N, which is the number of moles of solute. So this is very interesting because basically what it tells you, this is a colligative property. It doesn't really care what the species is. We talk about ionic species. It doesn't really care what it is. It just cares how much, and the charge. That becomes important. And depending on the charge, it depends exponentially on the charge. So some of the other things that are what we call colligative properties, it depends on the amount, not necessarily what it is, and the charge. Some of the other colligative properties will deal with a freezing point depression, okay, osmotic pressure. Now, if we think about this, one of the instruments that we use in developing formulations for injectable drugs is something to measure the tonicity. And basically, the tone of a cell is the shape of a blood cell, okay? If we add a solution around the blood cell that is very weak in salt concentration, what's going to happen is the cell wall of a blood cell is a semi-permeable membrane. So it sees a really low salt concentration around itself. It's going to bleed salt out of the interior of the cell to try to neutralize that, okay? So we see the cell shrink a little bit. However, if we see a high concentration, it's going to bleed water into the cell. Did I have that backwards? Well, anyway, what it does is it changes the shape of the cell based on the salt properties. So it's basically what we call, it changes the osmotic pressure. And we measure that through two things. We can measure the tonicity by vapor pressure, okay, or freezing point depression. So there's two instruments that we can use, okay. So by putting additives into our formulation solute, we change the osmotic pressure or the escaping tendency of those water molecules from a product. Also changes the boiling point, okay? So if we think about, if you've ever bought an instant cake and you read the back of the box, it says, you know, if you're at sea level, bake it at this temperature for this amount of time. If you're in the mountains, bake it at this temperature, because the boiling point of water between sea level and elevation in the mountains changes, okay, based on the pressure. So basically what I say is added salts can depress the freezing point of ice and significantly reduce the glass transition temperature. So if we've got an amorphous component in there, what we find is that the water, again, the salt will attract the water. And basically what happens is as the amorphous phase picks up more water, Water is a plasticizer, so we actually see the glass transition temperature decrease as we increase the salt concentration. Sometimes we've seen it decrease down to a point where we can't even freeze the product. So my rule of thumb is keep as much salt out of the product as you can. We've had clients that have come here for us to develop a formulation for them, or they have a formulation that's not performing well for freeze drying, and we look at it, it's got a ton of salt in it. And they say, well, let's take the salt out and maybe put it back in the reconstitution solution. So we freeze dry without the poor performing excipients, and then we add them back in, okay? So keep the salts to a minimum, try to avoid divalent and higher order species. Again, as I mentioned before, the charge, the amount and the charge will impact that effect on the formula, or on the glass transition temperature and the freezing point property. So sodium chloride, if we have to add a salt, sodium chloride, we don't want to use calcium or magnesium or anything with an iron, definitely not iron, +3. That will significantly reduce the vapor pressure. Salts increase the amount of unfrozen water. We can delay or sometimes prevent crystallization of other components. If we need to adjust tonicity, so say for example we had a client here that said it's got to be isotonic. Okay, it's got to be, and isotonic is the body's natural salt balance, if you will. We want to keep the formulation right within the body's natural balance. It reduces pain on injection, discomfort. We can adjust that with, say, a mannitol or a glycine. Now, it's not going to be as effective because, again, as I mentioned, the charge really is exponentially affecting the adjustment in tonicity. So it's going to take a little more mannitol or glycine, but we can bump it up. So we had one product here that I mentioned. They needed it isotonic. Well, just the normal formulation was very low. We didn't want to dump in a bunch of salt because then it was going to make it impossible to freeze dry. So we started adding mannitol and measuring. We have a vapor pressure osmometer here. We started measuring the tonicity, and we're able to get that up to, isotonicity with a mannitol addition. And actually, mannitol is what's known as a bulking agent. So we got a nice bulked up cake, looked good, met the tonicity requirements, and didn't really change the freeze drying character or make it difficult to freeze dry. Okay, let's talk a little bit about ice nucleation. Now, for years, this was one point in the lyophilization cycle we couldn't control. We can control product temperature through changing the shelf temperature, changing the chamber pressure. We could never control when things nucleate or freeze. If you've got a clear door in your freeze dryer, we have a Lexan door, polycarbonate door, I don't know. We can see our samples go through the freezing process, and it's like watching popcorn pop. You get one vial to freeze, minutes later you get another one freeze, so these are freezing at different temperatures and times. We've never been able to control that until recently. Now there's been studies that have been done, again Mike Bacow was a big innovator in this technology, ice fog. So basically we create a bunch of small ice crystals in a vapor, shoot it into the freeze dryer, these generate tiny ice crystals and essentially a seed crystals for nucleation. Vibration has worked, sonic vapor, again, not really practical. What SP has come up with, actually it was in combination with Praxair, a compressed gas company, is a way to control nucleation. Now what we see here is just a normal freezing. We see thermocouple probes in our samples. Now I will tell you, thermocouples act as sites of nucleation. So in this particular case, they tape the probes to the outside of the vial. But this is very typical. As we cool the product down, these vials start to freeze here. Boom, this one goes. I mean, we're talking, probably about an hour in time between when the final vial freezes on the shelf. That's a lot of time. And notice the difference in temperature. This one's about maybe -12 all the way down to below -20. That's a huge temperature difference. When things freeze quicker, so we build up a lot more supercooling here, your ice crystal size is going to be different. So we've got product in our freeze dryer that's got a vast difference in particle size of the ice crystals. These are going to control or freeze dry very differently, or can freeze dry differently. So this has been the normal course of business now. However, with the new controlled nucleation technology, look here. So we're cooling. We hit a point where we initiate the controlled nucleation, the control lyo technology, boom. Everything nucleates at the same time in temperature. How does this work? Basically, what SP has done is now the freeze dryer chamber of their development unit, their Lyostar 3, is now a certified pressure vessel. Previous units were not. So the way we do it is we cool the temperature of the product. I think it's usually negative, between 3 and 5 degrees C negative. It's still a liquid. Again, we talked about supercooling and freezing point depression, so we're still a liquid in here. Well, what they do is they apply a pressure to the chamber. They pressurize this chamber. Don't try this in your normal freeze dryer. Again, you'll blow the doors off. The Lyostar 3 with control lyo technology is a certified pressure vessel, so it can take the pressure. It's not a lot of pressure, but don't try this at home without a Lyostar 3. So they build up a certain amount of pressure in the chamber, and then boom, right here, they quickly release it. That causes nucleation, okay? So everything nucleates at the same time and temperature. It's much more uniform. Again, these are going to dry much more uniformly in primary drying. So controlled nucleation is quality by design. So SP with the Lyostar 3, we can control the nucleation event in both lab and production dryers. This is beautiful, okay? This technology can be added and removed on any unit with SIP within days. So it's basically, as long as you have a sanitary port of a certain size, you essentially just bolt this thing on. It's an inlet and pressure relief valve. There's nothing to it. Now you have to add the, again, the software portion of it, but it's not like you got to go through and completely retrofit your freeze dryer to add this technology. It's a quick bolt on. Then you'll have to go through your normal IQ, OQ, you know, all that validation protocol, but again, very non-invasive in regards to retrofitting a freeze dryer, assuming it's a pressure vessel. So what we see here are some experiments that were done to show you one of the benefits of controlled nucleation is controlling the particle size of the ice crystals. So again, I think I mentioned this before, how fast things freeze affects the crystal size. So if we build up a lot of supercooling and we get freezing that occurs very quickly, we tend to get a very small amount of small ice crystals and a high surface area of ice. And that's what we see here. With uncontrolled nucleation, we built up a lot more supercooling. So when things crystallized, it was very fast. So we get a high surface area of ice, very tiny ice crystals. However, with controlled nucleation, with SEM, we see these very wide pores. Now we like wide pores. It's a lot easier to get the water vapor out. This actually dries at a lower temperature. Okay, much more efficient in getting the water vapor out of the product. And this is a much less damaging environment for certain molecules like proteins. They don't like typically a high surface area of ice. So freezing affects the thickness of the ice channel walls, the size of the pores, can affect the rate of reconstitution of the dry powder. Again, freezing, how we freeze can denature certain sensitive proteins. So rate of freezing does matter, or can matter. Some protein formulations, like I mentioned before, fast freezing or, again, supercooling leads to very quick nucleation. We can damage some proteins if they're sensitive to it. Again, this just shows you a protein formulation we had in our lab, a native state in the liquid. If we do freeze-thaw studies, you can actually aggregate that protein to the point of you can actually physically visualize or physically see the aggregates. They aggregate out, precipitate. We see that as cloudiness. Okay, let's say a little bit about annealing. So we talked last time about a metastable glass forming. So it should have crystallized during the freezing phase. It didn't for a number of different reasons. So now we're left with this metastable glass that we have to get rid of. Annealing does that. So it's extremely important to make sure we don't leave our product with a metastable glass, okay? Because it will eventually crystallize and wreak havoc on our formulation. What is annealing? Basically annealing, we freeze the product down, we warm it up to a fixed temperature, we hold it for a certain amount of time, and this is all done at atmospheric pressure. So annealing step is actually part of the freezing phase, atmospheric pressure. We warm it up, hold it, we cool it back down, kick on the vacuum, then we're in primary drying. We can do annealing studies on the DSC. We can also do these on the freeze-dry microscope that we talked about last time in the last lecture series. On the DSC, if you recall from last time, very classic glass transition temperature, TG prime. Again, the S-curve. Very classic eutectic melt here. Very sharp symmetric peak. This is shows us a metastable system, okay? How do I know that? Well, I see a small TG prime. As we warm up, we see that crystallize. So again, down here, when we froze, we formed the metastable glass. As we warmed up, we go through the glass transition. Now those molecules start to move, and now they line up and form the crystal. Now, this tells me if I see this, I need to anneal the formulation. What temperature do I use? Well, I want to be above the glass transition temperature. I want to be above the crystallization event. I want to be somewhere here. What we see here, which we've cut off, that's the onset of the ice melt. So again, we're doing this on a liquid sample. We're not freeze drying this. We're just ramping down or ramping up. So we're starting to melt the ice. We don't want to start melting the ice. So we want to be somewhere right in here, above the glass transition, above the crystallization event, and not getting into the ice melt, right here. Now, the experiment that I do, the first time I run a sample on the DSC, if I see this, what I do is I say, okay, let's run it again. Now this time, I start at room temperature, I cool down, I warm up, and I only go to here. And I'll hold it 5 minutes. Now, we would not do this in a real environment with a vial full of 20 mils of liquid, but I'm dealing with about 15, 18 microliters of liquid in my DSC pan. I hold it here. Then I cool it back down. Now, I warm it up, and this time I go to room temperature. What should I expect to see? Well, we shouldn't see a glass transition. We've converted the glass to a eutectic. I shouldn't see the crystallization. There's nothing to crystallize. All I should see now is this on that second ramp up, where we're melting the eutectic that we formed right here. Perfect, okay? We can also do this on annealing, or I'm sorry, on the microscope. Now, we mentioned before that the microscope has a magenta filter, so this bumps everything up in our field of view 530 nanometers. So the magenta, if there's no crystalline species in, all we're going to see is a magenta. Now, as we see here, I don't see anything but magenta, excuse me, magenta. And that tells me nothing's crystalline. Now, if I warm the sample up and anneal it, now we start to see these colors, these bursts of color come in. And great. That tells me, as we've warmed up, we've caused that metastable glass to crystallize. Now the crystals are birefringence that we talked about last time. Now we see these alterations in color. Great. Okay, let's talk about primary drying. So the major function of primary drying, like we mentioned before, is removing ice in the ice channels. Again, as we talked about before, we get phase separation during freezing. We get pure ice in the ice channels. Everything else is squeezed around the ice channels in the interstitial space. Great. Once all the ice is gone in the ice channels, technically primary drying is done, and we're moving into secondary drying. The driving force of freeze drying. Most people think it's temperature. It's pressure. Okay, so it's basically at the sublimation front is where we're generating all this water vapor. Now the water vapor creates a area of high pressure. Okay, all that water vapor is a high pressure area. The surface of our condenser away from the product is extremely cold. So anytime any water vapor gets near it, it's going to crystallize and stick. So that's a low pressure area. That's the delta P that we're talking about that is driving freeze drying. If the vapor pressure, or if the pressure at the sublimation front equals the pressure in the chamber or at the condenser, freeze drying is going to stop, or at least it's going to progress extremely slowly. That's why we like that wide delta P, that change in pressure between the pressure at the sublimation front and the pressure the pressure at the condenser and the pressure at the sublimation front. Those are very wide. We're going to get water vapor flying off the product by gradient and going down and sticking to the condenser. So it's, again, false to assume that temperature is the driving force. The sublimation rate of ice, we can calculate this. Again, the rate is a force, or delta P, that we talked about, divided by the resistance. Now, there's a lot of resistance that we encounter in freeze-dried products. Resistance to heat transfer is one of them. Okay? Many factors contribute. So we can control the temperature of the thermal fluid in the shelf, okay? But we've got to get that temperature, that heat, up to the sublimation front. And we get a lot of resistance of heat as we go from the thermal fluid up to the sublimation front. We'll talk about some of those. The resistance to mass transfer. So once we generate the water vapor, so we've converted the ice to the water to the vapor, now we have to get that out of the product down to the condenser. Now the engineers in the room will say, wow, is it heat transfer limited or mass transfer limited? What's the limiting factor? We identify that, then we take steps to minimize the loss due to those resistance values. So freeze drying can take place at atmospheric pressure, as we mentioned. However, it's a very, very slow process. It's done by molecular diffusion against a pressure gradient, which is air. So it's a very, very slow process. Now, with vacuum technology, again, we can get that vacuum very low in the chamber, okay, and drive that by bulk flow, okay? So we generate the water vapor, you know, high pressure at the sublimation front, low pressure in the chamber, bam, that water flies off the product. And now instead of setting something out at atmospheric pressure and letting it dry over a course of months, we can do it in a course of days. Okay, so all transfer operations during primary drying heat and mass are described as a flow rate or a flux if we throw in a unit area. And again, as we mentioned before, it's a force divided by a resistance. Again, the engineering approach, again, is to understand what's the limiting factor and then take steps to reduce that. Now, this is where the engineers of the equipment, the vials, the stoppers come into play. Okay, there's a lot more science or a lot more engineering known about freeze drying operations these days than there used to be. So the guys at SP, the engineers, they know all these things. So when you buy a freeze dryer for them, they're taking all of this into account to minimize that resistance of all these factors. Now, when you go to buy a off-the-shelf development scale unit, again, it's a one-size-fits-all. And they have gone in and really optimized that process to minimize heat transfer loss and mass transfer resistance. When you go to buy a production scale unit, that is a made-to-order unit. And the engineers will tell you, you should do this or you should not do this. Listen to them. There are certain companies that have not, and it's come to bite them. So definitely listen to the engineers when they talk about designing the freeze dryers. We can do a quick calculation of the sublimation W of ice. It's a pretty simple process. So basically, we can measure the sublimation rate based on the vapor pressure in millimeters per mercury, which will change as a function of temperature. The molecular weight, 18 of water, and then the temperature in Kelvin. Now, if we assume a vial with an inner radius of 0.9 centimeters contains 2 grams of ice at negative 18 degrees C, so I don't think we've showed it in the last slide, or I'm sorry, in the last lecture, but we know the vapor pressure of ice is temperature. So SP, on the front of their development scale freeze dryers, has a nice vapor pressure over ice table as a function of temperature. So we just go to that table, say, well, if my ice is going to be held at negative 18, what's the vapor pressure? Well, in this particular case, it's 939 millimeters of mercury. So we plug that in. 1.45 times 10 to the negative 2 is our sublimation rate, grams per centimeter squared per second. Okay, great. That's easy to calculate. So, based on our example with the inner diameter of the vial, we plug in the sublimation rate to the time to dry 2 grams of ice, less than a minute. Well, we know that's not reality. The reason is, again, all the resistances that we encounter. In a perfect world, if there were no resistances, we could freeze dry ice in no problem at all, in no time at all. So this is just, I like this diagram because it shows you what's going on, both heat transfer and mass transfer. So again, we can control the thermal fluid in the shelf. However, we heat the shelf. However, we lose heat. So there's that stainless steel shelf we have to punch through. We lose heat. There's a gap of air here between the bottom of the vial and the shelf. We lose heat. Okay. There's all this ice we have to get the heat through, we lose heat, so that by the time we get the heat, excuse me, to the sublimation front, it's going to be drastically different than the temperature of the thermal fluid in the shelf due to all those resistance values. Now, okay, so here we get the heat up, we convert ice to vapor. The vapor's got to punch through the dried layer that's sitting off on top of it. There's resistance there. It's got to go through the neck of the vial, resistance there. It's got to travel through the tubes, resistance there before it gets to the condenser. So the question we have to ask, do we need to determine if our process is heat transfer limited or mass transfer limited to develop a good lyophilization cycle? The answer is no. And again, we're confident that the engineers at SP have designed the freeze dryer to minimize resistances both in heat transfer and mass transfer. Same thing with the guys in the vials, developing the vials and stoppers. Now, there are things that we can do as development scientists to minimize that. So, number one, always use tubing vials. They're much more uniform, they're closer to the shelf, better heat transfer. Also, don't fill the vials more than half full. Now you've got this huge slug of ice we got to get through. You get a very large dried layer. Now it's harder for that water vapor to punch out. If you have to fill the vial more than half full, go to a larger vial. Don't super concentrate your formulation. Again, my sort of rule of thumb is don't formulate more than 10% total solids, or 100 milligrams per mil, because again, then once you generate the water vapor, it's got to get through this brick of dried layer, and it's very difficult. So now remember, at atmospheric pressure and at modest vacuum levels, air is a good conductor of heat. Most of us are heating our homes with forced air. So at atmospheric pressure, we heat the air and we recirculate it, good heat transfer. This is not true at high vacuum levels. So the behavior of gases at low pressure or high vacuum, the transport properties change, and we can divide those into several different categories according to what we call the Knudsen number, after the guy that came up with this. So basically, the Knudsen number is defined as the ratio of the mean free path, we'll talk about that, L, of a molecule to a characteristic dimension. So if we think about a dimension, if we think about a pore in a freeze-dried cake, that would be the dimension A, okay, the diameter of that tube or that opening in the cake or in the pore. So if we say the mean free path is L divided by A, okay, we can calculate that Knudsen number. Now, the mean free path, basically what we're talking about is in a high pressure environment, the mean free path is you have one molecule that you're monitoring. How far does that molecule have to go before it bumps into another one? Well, at atmospheric pressure, we got a ton of stuff floating around in the air. Carbon dioxide, argon, nitrogen, oxygen, ton of these things packed in very tightly. So the molecule, the distance L, is very short, and it has to travel before it bumps into another one. However, so the mean free path L is very short. If we put a high vacuum or a low pressure in the chamber, we're pulling a lot of that out. So the mean free path, again, is going to be a lot longer, okay? So it's basically, again, a function of the temperature and the pressure in the chamber and the collision diameter of the molecule itself. So we talk about the Knudsen number, a function of the mean free path divided by A. Again, A is the diameter of the pore we're trying to get through. We solve it for a water molecule. Again, it's about 3 divided by the pressure for water vapor. So if the Knudsen number is very low, again, it's typically in a higher pressure system, so we get viscous flow. So the molecules are so tightly packed together, we actually have to talk about the viscosity of the gas in the equation. Molecular flow, we're at a high pressure environment. Again, the molecules are very far apart, high length before the molecules will bump into each other, and somewhere in the transitional flow is between those two. We can calculate the mean free path as a function of pressure for water vapor. Again, very easy. And again, as we notice, we get to a low pressure environment, the mean free path grows extremely high. I think this might be exponential. Don't believe. I think it's exponential. Don't quote me on that, what I'm trying to say. So basically, we can look at the mechanism or the ratio, again, the Knudsen number, as a function of the mean free path. So we know at a certain pressure for a water vapor what the mean free path is. The diameter of what we're trying to get, that becomes A. Okay, so trying to get through the dried product, the typical A or the pore size in the product is about 20 microns. So essentially, we're in Knudsen flow. Through the stopper, we get a much wider opening that puts us in transition flow. Again, changing pressure as well. And the chamber is huge. So we get into what's called viscous flow. So we get a lot of molecules floating around in the chamber. Conductance through a pore in the cake. So how easy, conductance F, or 1 over resistance, how easy is it to get a water molecule through the pore in the cake? If we're under viscous flow, again, a lot of molecules. The conductance, I'm not going to say too much about it other than focus on, again, the pressure, obviously, the radius. Okay, so this is the radius of the pore we're trying to get through. And again, as I mentioned before, it's a function of the viscosity. So there's so many molecules, the gas actually can become viscous, so we have to put in a variable for that. But the thing I want to focus on under viscous flow, it's a function of the radius and the length of the tube. So we talk about a freeze-dried product, and we talk about a path through the dried layer. The only way to mathematically explain it is by a bundle of straws together. So we know the diameter, we know the length. Okay. Now what you'll notice, the conductance, or how easy it is to get a water vapor through a pore in the cake, it's the radius to the 4th power. So the size is huge and how easy it is. So the larger we go, incredibly, it just makes it much more easier. Now what we'll notice, the length also plays a factor. So the larger the length, the longer the tube, the harder it is to get the water vapor out in viscous flow. Okay. So the engineers at SP, they're designing their freeze dryers. If you've got an external condenser unit, so a sample chamber and a separate condenser chamber connected by a tube, they're making those tubes very wide. Okay. They're also making them very short. Okay, to maximize the vapor flow through the throat of the dryer. Again, particle size in our freeze-dried cake, what we can control. The larger the particle size, the much easier it is going to get the water vapor out. Now, molecular flow, again, we don't have to consider the viscosity of the gas, but again, we do consider the opening of the pore, and again, cross-sectional area of the pore, great, divided by the length. Again, so these are factors. They do contribute as well. Under viscous flow, you'll notice it's the 4th power, again, so has a big impact on that. So we'll talk about heat transfer, again, getting the heat from the thermal fluid to the sublimation front, and again, where these are the resistances where we're losing heat. And we talked about those. And again, I love this. So the shelf temperature is about plus 42. By the time we get to the sublimation front, it's negative 20. Now this is pretty extreme because, again, we're assuming we have a lid on the pan. We're assuming we leave the pan, the vials on the pan. We've got a molded vial. We don't do this anymore. It used to be this extreme, but again, this just tells us why we put vials directly on the shelf. We don't use these molded vials because we can greatly reduce this. Okay, but still, we're going to see a fairly big temperature differential between thermal fluid in the shelf and the product temperature when we probe with our thermocouples. It may be, I've seen it as high as 25, 30 degrees C. So by far in freeze drying, heat transfer is the largest resistance in the freeze drying process. So, and a lot of it's due to that gap between the bottom of the vial and the shelf. And you'll notice here, if we go back to this diagram, this temperature here, at the bottom of the vial, about plus 32, getting into the vial or up to the sublimation front, negative 20. So, I'm sorry, here to here. So maybe about 15 to about negative 18. So that's the biggest. So anything we can do to minimize gaps of air between the bottom of the vial and the shelf is great. So don't use pans, use tubing vials. Again, heat transfer is the largest factor. We know that in freeze drying, there's different heat transfer mechanisms. By far, it's conduction. Again, we heat the surface of the shelf. The molecules will warm the bottom of the vial. That heat is transferred by conduction. We get a little bit from convection, a little bit from radiation, but by far conduction is the largest heat transfer mechanism in freeze drying. Okay, we talked about that. And again, be aware that each substance between the thermal fluid and the sublimation front is a resistance to heat transfer. So anything we can do to minimize that benefits us. We talk about the heat transfer by conduction governed by Fourier's law. So heat is a function of time. It's based on, again, dT, or the gradient of temperature, is a function of thickness of the material. The cross-sectional area that's exposed, so cross-sectional area at the bottom of the vial. K is the thermal conductivity. So each material is going to have a different thermal conductivity, or how easy it will transport heat. And just shows you the difference here between different materials. Borosilicate glass, thermal conductivity. Again, aluminum is through the roof. We know that aluminum conducts heat much easier than stainless steel. We don't construct our shelves or pans of aluminum because they just don't have the tensile strength. So heat, total heat flux, again, heat is a function of a cross-sectional area, is a delta T across the total heat loss, so across all those materials we put in the path between the thermal fluid and the sublimation front, and then we can sum the resistances from each of those. So we can calculate the resistance of each of those different materials. Okay, we can calculate the resistance from ice, glass. They've got an aluminum tray here. Again, it would be stainless steel, but we total those to sum up the total resistance. Let's talk about mass transfer too. We've talked about the resistance of heat. Now we have to talk about the resistance of mass. So once we generate the water molecules in vapor, how hard is it to get out of the cake? And again, it's a force, or pressure differences, divided by the difference resistances that water molecule encounters as it goes from the sublimation front to the condenser. And again, we talk about the resistance of the dried layer, getting out of the vial and stopper, getting through the chamber to the condenser. And again, what we find here, same thing we did with heat, the largest resistance we see of getting water vapor out is the dried layer. So again, it's, as development scientists, this is something we control. Don't, fill your vials more than half full. You get this huge slug of dried layer on top that it's hard to get the water vapor out, and don't super concentrate. Again, the more material you put in there, the harder it is for that water vapor to escape. Reality, the flow regime that we encounter, we talked about molecular flow, viscous flow. It's generally in the transition flow. And again, what we talked about too, properties of the different gas in viscous flow, we do have to consider the viscosity of the gas. But again, the conductance here we see again is C, which are geometry factors. Again, the radius essentially is built in there divided by the length. So the obvious take-home message, don't fill the vials more than half full, and don't super concentrate your samples. Again, no more than half full, filling, and then no more than 100 mg per mil or 10% total solids in the formulation. This is kind of my rule of thumb. And this just shows you, again, the thickness of the dried product. We know the resistance, this is resistance, increases. Again, resistance increases with the thickness, okay? But it also increases with the total solids content. We know that. So again, I'm not going to read through these. We've talked about that just to minimize the mass transfer and heat transfer resistance in primary drying. Okay, let's wrap it up here with secondary drying, then we'll open the floor up for questions. Secondary drying goes, or primary drying goes to secondary after all the frozen ice in the ice channels is gone. Once that's done, we're technically in secondary drying where we're removing the unfrozen water that we talked about in the last webinar. This is a busy slide, but it shows a lot. Basically, the rate of water loss versus time. So again, at the start of primary drying, we see our greatest water loss decreases as we go. Again, we ramp the product temperature. We see the rate decrease. Obviously, temperature is really the driving force in driving the residual water off in secondary drying. Product temperature, again, we raise. Water content goes down really quickly and then kind of levels off and slows down. So we see the largest burst of water as we start secondary drying, as we ramp up the temperature. And we can actually see that if our freeze dryer has a Piranha gauge, which we don't. I don't have a slide of that here, but the start of primary drying, you'll see your Piranha gauge spike. That's not uncommon. And then settle down as we slow down the water release in secondary drying. This just shows you that 1 minus F, that's a drying factor, very wet up here, very dry. So what we used to do in freeze drying was in secondary drying, we'd ramp the temperature up, we still do that, and then we drop the pressure as low as it could go. We don't do that anymore. And this just shows you the drying time if we change the pressure. And there's a slight difference, but it's not enough to change your cycle. So that's why we don't alter the pressure anymore. We just ramp the temperature, keep the same pressure we determined. Residual moisture in the final product, we try to typically get to less than 1% for small molecule. Larger molecules, we might be somewhere 2 to 4 to 5%. And again, Carl Fisher is the method of choice that we use for residual moisture. It's very sensitive. Coulometric Carl Fisher, don't use volumetric, okay? We've also been able to use IR. NMR has also been viable for residual moisture. The residual moisture affects the glass transition. So in our lab, we can measure the TG. So we go to the dried solids measuring the glass transition. It's now TG instead of TG prime. We can also measure that on our DSC. So we measure the moisture content in the Carl Fisher. We put a sample of the dried material in our DSC. We can measure the TG. That affects the higher the water vapor, the lower the TG. Be aware moisture leaching from the stoppers can affect the product. So you want to make sure for a freeze-dried product and make sure you dry your stoppers appropriately. Okay, we'll open the floor up for questions. And again, I always leave my contact info. You can reach me by email or give me a call if there's any questions outside of this. So let me make sure I've got everything set up appropriately here. And you can go ahead and type your questions in the spot provided. Oh, here we go. Oh, good. Okay, first question. How do we determine the temperature of secondary drying? That's a great question. Basically, what I do when I develop a cycle for a client is I look at the thermal stability of the molecule. So say the bulk producer of the molecule, I'll call them up at the API and say, what's the thermal stability? They hopefully by now, once they've got the manufacturing process, they've done a stability profile of the API. They say, what's the thermal stability of the API? In some cases, they've said, don't take it over 30 degrees. Okay, well, then I'm not going to take my product temperature I'll probably start secondary drying about plus 20. I've had some manufacturers come back and say, hey, you can stake this stuff up over 80 degrees C and it'll sit all day without any degradation. Well, then I'm going to go to the extreme because, like I mentioned, the driving force of secondary drying is really temperature. So that's how we base it. Now, biologically based molecules, proteins, generally you're going to stay about in the 20 to 25 range. But small molecule, call the manufacturer. They should have some information. Next question, is there risk of contamination in the vapor nucleation method? No, I wouldn't say so. I mean, you might be able to maybe elaborate that on a little bit more, but you know, anytime we pressurize, at least on a sterile system, all that air in and out goes through a sterile filter, so we're not exchanging room air. So if you're talking about contamination from microorganisms, no, it's all filtered air. Let's see. I have a question regarding differences in drying of small molecules and large molecules. Well, that's a great question too, and a lot that we deal with in our facility because we see stuff all over the place. Small molecule, large molecule, and yes, they are typically very different. Cycle or formulation development is very different. I don't do anything differently in regards to cycle design. I mean, it's all based on, cycle design is based on your formulation. So we develop the cycle around the formulation. In regards to secondary drying, yes, we have to be very careful generally, so we're not, taking secondary drying up to 50 or 60 degrees. We have to keep that in check. So generally 20 to 25 in secondary drying, it works for us. Again, primary drying is going to be all over the board. It's done at sub-zero temperature, so it's not really an issue. Again, the more stabilizing effect of a large molecule is how you formulate. So what stabilizers do you put in there, surfactants, etc.